Hi, good morning, everyone. My name is Xinwei Mao. It's my pleasure to be here to present to you the research and development effort at the center to support this phosphorus initiative. How can I go back? Oh, sorry. Okay. All right. So our work is organized around these three complementary areas, which include the field monitoring, commercial products validation, and a novel technology development. So basically, take all these activities will allow us to move from understanding the phosphorus problem to really implementing the solutions. So before I get started, I would really like to acknowledge many of the scientists, students, engineers, collaborators who have contributed to all these research areas. So it's truly a team effort. It's my honor to present all these accomplishments from our entire team. So with that overview, I'm going to start with the first part of my presentation to focus on our effort for field monitoring. By doing this project, we are able to understand the phosphorus behavior in on-site wastewater treatment systems and understand their fate and transport in the surrounding environment of on-site systems. So over the past few years, we have been conducting two parallel field investigations. One is locally on Long Island that we have been monitoring the phosphorus removal by the NRBs, which you have heard a lot about the NRBs. The other one, we have been working in the upstate New York to look into the phosphorus fate and transport in the surrounding environment of conventional on-site wastewater treatment systems. So let's first take a look at our effort on the NRB monitoring. So as you can Oh, I don't know why these do not show up, but basically there's this very busy figure. We have been monitoring the NRB's performance for their phosphorus removal over the past 3 years. We have been conducting quarterly monitoring. So it's supposed to be a very busy figure. What I'm trying to show you is that the influent phosphorus level from the septic tank effluent is really fluctuating over time. But if we summarize what we have seen in this monitoring, sorry. This is supposed to be a summary slide. Basically, what I'm trying to tell you is that for all these three types of the configurations, they have shown a substantial phosphorus removal in the range of 60% to 80%. So basically, the data tells us these NRBs not only remove nitrogen as they are supposed to do, they can also remove a substantial level of phosphorus. So the question becomes, where are these phosphorus being retained in which unit? And would these retention be sustainable over time? So in order to answer this question, so we conducted two parallel studies really to evaluate these two separate units, the nitrification unit and the denitrification unit. And also we compare the system performance between the newly installed NRBs and the aged NRBs. We try to understand where this phosphorus is being retained and where these can be released to the environment. To understand this phosphorus flux is very critical for us because if they are really finally leaching from NRBs, we are going to design a final polishing unit to capture that phosphorus. So let's first take a look at the performance of the nitrification unit. So basically what we did is we constructed several lab-scale columns using aged sand and fresh sand. We apply septic tank effluent to all these columns. So basically, this figure would show you that for the aged sand, they can remove roughly 50% of the total phosphorus from the septic tank effluent, while the new sand can remove roughly about 30%. So basically, we also applied the synthetic rainwater to mimic the natural precipitation. So basically, we also observed that those phosphorus can be leached out from no matter aged sand or fresh sand. So basically, these results tells us this phosphorus retention in the nitrification unit is temporary. So there's a potential for that phosphorus to be remobilized. So the same trend was observed in the denitrification unit as well. So we also constructed parallel wood chip reactors using fresh wood chip, aged wood chip as well as the wood chip that has been in storage for a couple of years. So basically, we applied these nitrified effluent, which will enter our denitrification unit in our pilot testing columns. We also changed the phosphorus levels in this nitrified effluent, and we later on applied a synthetic stormwater to see if those phosphorus can be leached out. So as you can see here in the summary, so we found out in terms of phosphorus removal, so the storage wood chip can remove the most of the phosphorus, which followed by the fresh and aged wood chips. And when we look at the potential of phosphorus release, actually the aged wood chips can release the significant amount of phosphorus. So basically what these results tells us is that the denitrification unit can also temporarily retain phosphorus. And also the capacity of this retention is strongly impacted by the age of the systems. So taking together these two studies, it tells us that directly actually motivated our subsequent effort to develop a polishing unit to really capture that phosphorus. So the other study that we conducted in the upstate New York is trying to help us understand if the phosphorus leaves the on-site system when it enters the environment, how would that move in the surrounding environment. So in order to answer this question, so we identified a few study sites in the Lake Como, which is a sub-watershed of Lake Cayuga. So we selected a few study sites which represent a different land use setting, including a farmland, a forest, as well as wetland. So in these study sites, we have been monitoring the groundwater, and also we collected like soil core samples, lake waters. We also conducted statistical analysis with the results we obtained. So on the right, I will give you an example of one site that with the farmland, close to a farmland. So basically, you can see here is the groundwater flow direction. So we collected soil samples between the drain field and the lake water. And in the upstream, we also collected a control sample to analyze these like soil profiles. So in the next slide, I can show you from a side view where we collect all those soil samples. You can see here is the control sample, and depending on the location of our soil cores, we collected like a close to the drain field, medium distance, and also the further from the drain field. So for all the samples we collected, you can see we collected at different depths, and all the samples we tested their total phosphorus content as well as the background metal concentrations. So in the next slide, here is a very busy slide. You can see several data sets, but I would like to focus your attention to the blue line. I think the first one is missing, but you can see there are some blue lines showing you the total phosphorus concentration at the different depths of these 4 locations. So basically, when septic tank effluent enters the drain field, you will see the total phosphorus level increase for almost 60% compared with the control site. And also, you can see this total phosphorus level will decrease as you go further from the drain field. So this is a directly very clear pattern to show you this wastewater impacted phosphorus plume close at this like watershed. And also, we found these the decrease of this total phosphorus concentration with a distance increase, and also because there's a clay layer at the bottom of this specific study site. So the concentration of the total phosphorus increase when it gets close to the clay layer. So now we understand that there is a phosphorus plume at this study site. So another question come up is, can we tell which factors really control these total phosphorus levels, like high or low, and how much it will move? So we conducted a series of statistical analysis. So basically what we found from our initial analysis is that certain like metals such as calcium, magnesium, and iron, so their concentration will increase as the depths increase at the study site. But the correlation between the total phosphorus to those metal oxides concentrations would vary at different horizontal locations, which tells us at this specific site is the phosphorus level, total phosphorus levels, is highly impacted by the specific site conditions, by the geochemical conditions. So based on what we have found from these field studies, our current effort will continue to conduct these lab-scale column controlled environments, continue our field investigation. In parallel, we're now using the AI and the machine learning tools to help us to dig into the tons of thousands of manuscript or literatures to help us to identify those primary factors may govern the total phosphorus levels. In parallel, we're also working on the feed transport models that will help us to improve our ability to predict the total phosphorus, the presence and their mobility. And these tools will also help us to identify the locations where have the greatest risk of the phosphorus loss, and can also help us and guide us to select the best technology that we can put at that study site. So now from the field monitoring effort, now the question becomes, is there any phosphorus removal technology available on the market that can really solve the problem? So now I'm going to move to my second section of the presentation to look at these commercial products validation. So over the past few years, one of the very important lessons we have learned is that for this phosphorus from on-site wastewater systems, when we look at their presence, attenuation, and mobilization, it is really impacted by very complicated geochemical conditions, and also like the groundwater flow velocity, the housing density, and so on. So that means there's no single solution that can be applied everywhere. So in order to apply such a technology to solve the problem, we have to be very site-specific. So that is the reason that the center has established an independent evaluation program that we can evaluate the current commercial available products and to identify their advantage, limitations, and where is the best scenario for that technology to be applied. So in this slide, here is a table to show you a summary of certain commercial technologies that are currently available on the market. So depending on their removal mechanism, we can group them into three categories. They are filter-based media, electrochemical technology, and also metal dosing technologies. So today I'm going to give you two quick examples to show you two of the technologies that the center is currently actively evaluating. So the first one is called a polonite filter. So polonite is a product, is a mineral filter that is produced from Poland. This product has been widely used in the North Europe, and it serves as a polishing unit at the end of the treatment train of on-site wastewater treatment unit. So at the center, we use polonite as a benchmark. So in the research trailer, we have constructed like a pilot scale testing. We're testing this media using different hydraulic loadings and different flow configurations, either upflow saturated condition or downflow gravity-driven conditions. We're also testing the filter's performance by treating different types of wastewater, like a raw wastewater or nitrified effluent or denitrified effluent. So we have conducted this pilot testing for over 500 days. So here is a brief overview of the filter's performance. As you can see, we are testing the filter with all three different types of wastewater. And the y-axis shows you the phosphorus removal efficiency. So basically, we found this filter performs very well, that it can achieve about 99% of phosphorus removal. But if you compare the different wastewater source, it works the best when you treat it denitrified effluent. It constantly showing us like over 99% of removal. And also, if we extend the hydraulic residence time, which means that when the system size is a little bit bigger, so you can really extend the system longevity. So basically, we use this benchmark of polonite to serve as the comparison base. So we developed a SOP so we can compare other commercial products to see their performance compared with the polonite. So now we know this polonite really did a good job to remove phosphorus, but we also have another question, like how much phosphorus this material can retain. It is a very important question because it will help us to decide what is the maintaining frequency, right? When do we need to replace the filter? And is there any potential to really to recover phosphorus from this filter? So in this slide, you can see all these columns are color-coded. Sorry, I think I need to get familiar with my pointer. So how can I go back? Right, okay. So basically, these columns are color-coded. So the darker the color means the more phosphorus it has attenuated. So basically, you can see here that in the upflow configuration, so in these, like a blue color means there are more phosphorus being retained. So basically, when we are treating nitrified effluent and denitrified effluent, most of the phosphorus are attenuated at the most. So this also agrees with our physical-chemical experimental data that when we use polonite to treat denitrified effluent, it will give us the best performance. So another commercial products, the electrochemical technology is, we're also testing this. So basically, electrochemical approach provide us a alternative which is very compact and highly controllable unit that can be integrated into the current IA system. As you can see, the basic mechanism on the top left is the figure showing you when we apply a low current density. So in the electrode, especially on the red color, the anode, it will release metal ions. It can be iron or can be aluminum. So this metal iron will precipitate a phosphate as a precipitate and can be removed from the wastewater. So there are a couple of companies who have these like products. The center is currently working with FujiClean to move forward on the field installation and evaluation. So my colleague will talk more on those details in the following presentation, so I'm going to leave it here. So although these commercial technologies have demonstrated very good performance, like show some the promise, but there are still opportunities like for us to continue to research and develop like new technologies in order to improve the removal efficiency, lower the cost, and also provide the potential to recover phosphorus. So as a center, when we visualize the next generation of IA systems, we think our system will not only remove nitrogen and the phosphorus, but also we would like to provide this opportunity really to transform phosphorus from a pollutant to a recoverable resources. And also in the meantime, in order to control the system performance, to extend its longevity and to have a better management, we also need to couple the in-situ monitoring technologies. So that is why in the R&D effort, we are currently working in parallel on three areas. The first one is the novel phosphorus removal media development. We're also working on this electrochemical technology to use it as a phosphorus recovery unit. And also, we're developing in-situ phosphorus sensors that can be used to detect phosphorus at different levels. So I'm going to start with this first one, the bio-based material for phosphorus removal. So here we use the material oyster shell. So oyster shell is produced in large quantity from the seafood industry as a waste. So basically, recent years, people have put some effort to repurpose the oyster shell to apply it to the coastal resiliency applications. But at the center, when we look at oyster shell, we take it as a potential candidate to help us to remove and recover phosphorus. So this is from actually a very simple chemical conversion. So if you heat up the oyster shell at a certain high temperature, so the main components, which is calcium carbonate, will be converted to calcium oxide, which is a very active media that will react with the phosphorus and precipitate it down. So our initial work was to optimize the thermal conversion conditions in order to make this work. You can see in this figure that when we increase the temperature to over 800 degrees Celsius, our product can remove almost 100% of phosphorus, no matter the production process involved oxygen or not involved oxygen. So compared with the raw oyster shell, here, if we do not do any modification, it can only remove less than 20% of the phosphorus. But the challenge here is how do we really apply this material? So as you know, calcium oxide is very active. It will dissolve in the water right away. And as a powdered form, how could we integrate it to our passive filter systems? So what we did, the team, we invented a novel approach by using this we call it a one-pot synthesis of calcium oxide-loaded granular porous media. So what happened is we would integrate the oyster shell and with wood chips as well as some like a binding reagent like a starch. So we will form some granules and we heat it up together. So by doing that, the calcium oxide will be captured in this very complex carbon network. So then when we apply it to a flow-through columns, the calcium will be gradually released and to react with the phosphorus. As you can see on the right side, so when we apply real on-site wastewater to test their performance, they can really remove over 99% of phosphorus. So in order to validate this process, we scale it up in our research trailer, and you can see this is how we synthesize all those granules in the lab, and we also constructed the columns in the research trailer by applying the real on-site wastewater to test our columns. So basically, these media can remove the phosphorus to over 99% for a continuous flow condition 24/7 over 70 days. And also here I show you some of the photos. These are the media before and after the treatment. So you can see these like white coatings indicate this phosphorus has been removed as a precipitate. But we did not stop at the phosphorus removal. As I mentioned, we also look into the potential if we can recover those phosphorus from this media. So in this slide, you can see all the different color bars. These color bars represent how much phosphorus can be recovered from this spent media. So we conducted mass balance, and we figured out that almost like 70 to 90% of those retained phosphorus can be recovered for agricultural purpose. So that really indicates the great reuse potential of this media. So I think for this is just example I want to share with you. The center is also working on other potential bio-waste conversion like filter media such as cellulose. You will see some of the posters. But these material development really feed our long-term goal that we not only are going to address this phosphorus pollution issue, we're also addressing multiple challenges at the same time by addressing this like a bio-waste repurpose and also to produce like a nutrients recovery as well as these like new fertilizers production. So as I mentioned, this is the passive filter that we developed. So there's an alternative approach that when we think about to recover phosphorus is to repurpose this electrocoagulation unit to use it as a polishing module at the end of the treatment tray. So our work has been started from our bench scale optimization analysis that we started from selecting the best combination of the electrodes that will give us the best phosphorus removal performance. And then those best working conditions such as the current density or the electrodes types and also the distance between the electrodes will help us to design our pilot scale studies. So now we're at the stage of pilot testing our best combinations of the electrodes. So our ultimate goal is to deploy this polishing unit to really recover phosphorus at the end of our treatment tray. So here I want to show you very briefly. I think that figure didn't show up. But basically, we are testing these electrodes, like we fabricate them in-house. Currently, we test these electrodes in a batch condition. And over 4 hours operation, very short period of time, we can achieve over 99% of total phosphorus removal from the wastewater. So these are a few photos showing you like how we fabricate and assembled our pilot scale EC unit. And we are currently evaluating the co-contaminants removal together with the phosphorus. And also we are identifying the best way really to capture the phosphorus from the final effluent. So as I mentioned, so in order to really develop this next generation IA system, we will not stop at technology on the phosphorus removal recovery. It's equally important to develop these in-situ monitoring tools in order to help us to make this system really intelligent. So basically, the center is currently developing 2 parallel like in-situ phosphorus sensors. The first one, as you can see here, this is based on the standard or classical chemical ascorbic acid method, which is a colorimetric method. So we have developed a prototype that we can measure the phosphorus concentration and the ppm levels. So the unique feature of this system is that they can do self-calibration after every 20 cycles of operation that will significantly increase the accuracy and the stability of this sensor. So the latest version of this prototype is currently under fabrication. We expect to get the new version by this summer. So another very exciting in situ sensor we're working on is this nanodot-based phosphorus sensor that based on the fluorescence emission. So it looks very complicated in this figure, but I would like you to think about this sensor as like a light switch. So basically, after we synthesize these nanodots, so it can absorb and emit like fluorescence. But on purpose, we provided some like a blocking components and reagent here. If phosphorus is present in the water, phosphorus will work and combine those blocking reagent, and then the light will come back. So basically, the lighter the image is means the more phosphorus is present in the water. Just because of this very unique feature, we can really tuning up the sensitivity of our sensor and also to adjust the test range of these sensor. We also have validated this sensor performance by using the real environmental samples that we collected from our upstate field study. So we have validated using this like a sensor. You can see here, this like a red color indicate our sensor measurement has a very strong agreement with our conventional analytical test. So our ongoing effort for our R&D, we will continue to investigate on these three parallel projects. We'll definitely focus more on the phosphorus recovery, co-contaminants removal, and the field deployment. So as the take-home message, I'm not going to read all the bullet points, but I just want to emphasize what I have covered so far for these three complementary areas that we're working on. From the field work, we found out that conventional IA system will temporarily retain phosphorus, but they can finally release to the environment. And when phosphorus gets to the environment, the fate and the transport of phosphorus is strongly affected by the natural specific site conditions. We have identified a few promising commercial technologies that can be used to remove phosphorus. We are also developing some very exciting filter-based media, electrocoagulation module, as well as the in situ sensor development. So taking these together, this will fulfill our long-term goal, really to transform phosphorus from a pollutant really to a recoverable resource, and in the meantime to provide, to protect our sensitive water quality using this integrated and sustainable wastewater management. So that's all of my presentation. Thank you.